The detection transformer, or DETR for short, is an early successful attempt at using transformers for object detection. It's a bit of a hybrid architecture in that it still employs a convolutional backbone for feature extraction and feeds those features into the transformer. For this video, the bit we are interested in is shown in this figure, which visualizes the attention map from the transformer's final encoder layer. It appears to have learned to separate semantic instances in the input image, and this is without explicit segmentation supervision. This network's trained to regress bounding boxes. We'll recreate an interactive version of this attention visualization by inspecting the intermediate outputs of the DETR model. More broadly, we'll see how you can poke around the internals of a neural network and go on your own explorations. We'll be using the Scripton Python IDE and its built-in visualization features, which are particularly handy for investigations like this one. You can download it from scripton.dev if you want to follow along. Okay, let's dive in. We'll use the implementation of DETR included in Hugging Face's Transformers library. As we saw, the DETR architecture involves a convolutional backbone for extracting the input image features. The paper tries two model variants, ResNet 50 and 101. The ResNet 50 variant should be sufficient for our purposes. We'll load up a test image, pre-process it, and feed it into the network. We'll also nest the forward pass within a no-grad, since we don't care about computing the gradients. Let's run it. It should be quick, and it's done. We can now inspect the outputs. First, here's our model. It's a PyTorch NN module instance, and Scripton has visualized its nested tree of submodules for us. We'll come back to this in a bit. Here's the test input image we loaded, and the output containing the class legits and the bounding box predictions. We can visualize these real quick using Scripton's canvas functionality to sanity check the results. Let's switch over to the REPL and post-process the raw outputs to get bounding boxes with high confidence in our image's coordinate space. We get two detections, presumably one for each dog. That seems promising. We can visualize these using Scripton's built-in Canvas toolkit. This is automatically available when running within Scripton. No need to install anything. We'll create a canvas from the image and then draw the bounding box for each detection on top. Cool, that looks reasonable. Now, let's switch back to the model architecture for a moment. Let's open it in its own tab to make things a bit easier. Here, we can see the various parts of the architecture, starting with the ResNet 50 convolutional backbone. Its output is flattened and fed into the encoder, which we see here is a stack of 6 of these attention modules. That's followed by a decoder, another stack of 6, this time with self and cross attention. Finally, we have the feed-forward networks at the end. So, for instance, this network predicts the bounding boxes we just visualized. Now, the attention maps being visualized in the paper are specified as coming from the last encoder block. Luckily, if you peek at the additional options accepted by the transformers implementation, you'll notice a promising output attentions flag. Let's set that to true. Scripton has a feature that lets us selectively run parts of the script called code sections. To create a section, simply add a colon after any Python comment. This turns the comment into a section boundary, and you can selectively execute just that section, or everything below, or above it. Let's rerun just the forward pass. The output now includes the encoder attention. There are 6 of these tensors, one for each of the encoder module we just saw. Let's look at its shape. It has 1 for the batch size and 8 for the number of attention heads. Now, 950 comes from the flattened convolutional features. So it's effectively the product of the convolutional features' height and width. We need these dimensions to reshape these back into a spatial form for visualization, like in the paper. So, let's navigate through the transformers library code and set a breakpoint right before those spatial features are flattened. Okay, here we see the features are getting extracted by the ResNet 50 backbone, and this is where it gets flattened. So let's place a breakpoint around here and rerun it. Okay, we've hit the breakpoint, and Scripton shows us the tensor shapes inline. We see its height is 25 and width is 38. And 25 times 38 is 950, so everything checks out. To follow the paper, let's get the attention of the last encoder layer. The script.show function can display 2D slices of tensors, or matrices, as color-mapped images. This first index corresponds to the batch. There's only one here. The second one corresponds to the attention head. There are 8, and we are picking the first one for now. The last one corresponds to a spatial position in the input. Recall that the paper picks 4 of these positions over animals in the image to visualize. We'll just pick 0 for now, corresponding to the top left corner. And the third one is the attention for that position. We'll take the whole slice here. This is a 950 dimensional vector, which we can reshape into a 25 by 38 matrix. And there's no clear structure for this position. This isn't particularly surprising. The top left pixel doesn't correspond to any object in our image. Now, if you're investigating possible signs of structure in these attention maps, one quick thing we can do is visualize them for all possible positions, all 950 of them. So let's do exactly that. Scrolling through these, we can see the familiar silhouettes immediately. To better appreciate the positional dependency, it'd be nice to be able to move your mouse over the input image and see the attention for that position. It'd also be nice to sweep through the different attention heads. So let's extend our script to do precisely that. We'll add in the couple of imports we've been using and start implementing a function that interactively visualizes the attention. We'll introduce 2 visualization state parameters, the attention head to visualize and the location of the pixel being visualized as normalized coordinates between 0 and 1. Next, let's write a function that re-renders the attention based on the current state. Let's have the title show the current attention head and position as well. This key argument causes Scripton to update the same visualization instead of creating a new one every time the function is called. Let's quickly run through and test things so far. Okay, that looks good. Now, let's implement the interactive bits. First, we'll create a canvas containing the input image, like we did before. We'll specify an onHover event handler, which is invoked whenever the mouse moves over the canvas. This will update the position state. And an onKeyDown event handler, which will change the attention head. And then hand over control to the canvas. The update attention position callback is passed an event which contains the current normalized mouse position relative to the canvas. We simply set our position state to that and re-render. Similarly, for the update attention head function, if a number key between 0 and 7 is pressed, we'll switch the attention head to it and re-render. That's all we need. Let's run it. And now we can see that the attention does indeed seem to focus on the object at each position. But what about other attention heads? This attention head seems to have this horizontal scanning behavior, while this one's vertical. And this one seems to behave like a bit of an attention flashlight. One question you could ask is, where does this instance separation first emerge? Is it in the transformer encoders? What about the convolutional backbone? Typically, these features are treated as black boxes. But similar to the attention, we can just visualize all 2048 of these. And as we scroll through the feature maps, we can see some familiar structure. So, one possibility is that the instance separation emerges in the convolutional backbone, and the transformer introduces a positional mapping for these instances in a way that's useful for detection. Thank you for watching, and I hope this video encourages you to go on your own explorations.